Okay, so let's get started with this lecture. So the things that you need to remember from the previous lectures are two things. One, we started from our 4-resistor network. So in particular, that looks something like this. So you have a resistor, another resistor, and then you have a gate. And then we added another resistor, and we call this RS, and we call this RD. And then we connected all of this to what we call VDD. And then we have VSS as our circuit. And in particular, from the last lecture, when we looked at this biasing network, we started looking at what we called our load line. And in particular, we said that if we looked at ID as a function of VDS, it had to behave like a line, which meant that if VDS is 0, ID had to be VDD minus VSS divided by RD plus RS. And ID is 0, VS had to be equal to VDD minus VSS. Since we knew the point, we knew the operation of this particular set was had it in load line connecting the points. Additionally, we said that in order to know where along the line our circuit would be operating, we would have to know what VGS is, which is V minus ES. And if VGS was less than V told, ID is 0. So let's just kind of draw a graph. So V threshold. We said if VG was less than V threshold, in that particular case, so this is VGS and this VDS, I would be 0. That meant that the operating point is here. This is VS less than V threshold. And then this is what VS is. This is VDD minus VS. VR cutoff rate. And then said that as we keep increasing VS, we're going to get lines that higher and higher. So this is VGS2, and then the VGS3, and as we keep increasing VGS, operating point, our VGS operating point will decrease. So eventually, operating point will be in the diode region, and there VGS between VGS, VDS to decrease 0 very slow. So this will be the saturation region, and then have tri region. So this is force approximate because this is more rounded, and this will round it like that. Okay. In particular, what we said was that based on this load line, what we would want to do is bias our transistor to have a DC operating point near the center of saturation. So this was our DC operating point. And then when we varied VGS about that point, we would get a change in VDS that approximately varies linearly. So, and that's what we call the small signal model. And the slope of this line is actually GM. So at this point, you don't really need to know the precise math of the derivation of the small signal model, but you should intuitively understand this picture. You should know why we want to operate near the center, and then why we want to have a small signal if we want to maintain linearity, or so that our small signal model is valid. Additionally, what we said was that if our VGS varied too much from the quality point, so if our signal was not small anymore, this would lead to distortion, clipping, nonlinearity, and all kinds of non-ideal behaviors. So if our device, our input signal, is operating such that it uses this region and this region, we're going to run into troubles in our amplification. And so that's why we have to make sure that our input signal is small enough so that our amplifier, so that our small signal model is valid. Okay, so you should basically understand what I just described. If you had a little trouble with this Taylor expansion derivation of the small signal model, that's fine, but you should at least intuitively understand that what we're really deriving when we look at that Taylor expansion is the equation of this line, and in particular, if our small signal becomes too large, then we're going to be operating near cutoff or the triode region, and as a result, we're going to get distortion and nonlinearity. So in this particular, we're actually going to use small signal model and small signal model. This is actually to learn math in order to analyze stage fire circuits, and in particular, class focused on common source, common drain, common configuration. Okay, so let's get started. Okay, so by the end of this class, you should be a professional in what we're going to call MOS, small signal analysis. And this particular slide summarizes all of the steps. And we're going to go over a number of steps of a number of examples applying this small signal analysis so that you actually learn how to use it. So in particular, what we're going to do is first, we're going to solve for our DC bias point. And to do that, we're going to look at our MOS circuits. And if there are any capacitors, we're going to treat them as open. If there are any inductors, we're going to treat them as short. In this class, there actually won't be any inductors, but if you did have an inductor in your circuit, you would treat it as a short. And then we're going to inactivate all AC sources, which for voltage sources means to short them. So in particular, if you look at a voltage source, inactivating it would mean that you put 0 volts through it. Well, a 0 volt drop is the same as a short. And then to inactivate a current source, well, you would assume that 0 amps flow through it. And if 0 amps flow through something, well, that's just an open. So whenever you want to inactivate a voltage source, you replace it with a short. And when you want to inactivate a current source, you're going to treat it as an open. So we're going to first derive our AC circuit model, inactivating all AC sources, opening capacitors, and shorting inductors. And we're always going to assume that lambda is 0 when we do our DC analysis. It doesn't matter what lambda they gave you in the original question. Once we have that circuit, we will determine ID from that circuit. And once we know ID, we will use this formula to determine our transconductance for our small signal model and our RO for our small signal model. This is the only place where you assume lambda is non-zero. So if you're given a non-zero lambda, this is where you use it. And in this class, we don't actually use this notation, but in some data sheets, you might not see a lambda. What you might see is VA, which is the early voltage, and that's actually equal to 1 over lambda. So in real life, if you find a transistor and you can't find the lambda, look for the VA parameter, or what people call the early voltage, and that's actually just 1 over lambda. It's just different notations other people will use. But in this class, we will strictly use lambda. Finally, tomorrow I'll talk a little bit about, next lecture I'll talk a little bit about the intrinsic gain of a transistor, which is equal to GM times RO. But that's next lecture. You don't really need this to solve circuits. So once you have GM and RO, what you will do is now write your small signal circuit, which involves shorting all capacitors, opening all inductors, and then you inactivate DC sources, which means you take a DC voltage source, you replace it with a short, AC current source, you replace it with an open, and then you connect your circuit and you replace your transistor model with either a pi model or a T model. This class we're not going to use the T model, but if you ever see one, these two circuits are equivalent. So in all of the circuits that I derived today, that I designed, that I show you today, I could equivalently use this T model and I would get the same answer. Sometimes people will use T model because it's more convenient and it leads to easier mesh and nodal analysis. That being said, in this class, we're going to strictly use this pi model. I'm just telling you that there's the existence of this T model. Okay, so this might sound very complicated to you, but now we're going to start going over a number of examples, and hopefully by the end of this lecture, you kind of get what I mean by opening and shorting inductors, and what I mean by analyzing your DC bias points and solving the small circuit model. Okay, so now let's analyze this circuit, which we actually analyzed in the previous lecture, and we graphically determined that the gain of this circuit, or little v ds over VGS, was actually equal to -10. So if you recollect in the previous lecture, when we put in 0.25 sine 2 pi t over 10 for little VGS, what we got was that little VDS was 2.5 sine, -2.5, sorry, 2 pi t over 10. And so we determined that the ratio of VGS to VDS was actually -10. So yeah, so this. Now we're actually going to use our small signal analysis to derive this. Okay, so as our first step, we need to figure out what our DC bias point is, or what capital ID is. And so to do that, we need to open capacitors and short inductors. Well, there's no capacitors or inductors in this circuit, so we don't have to do anything. And then we need to inactivate AC sources, which means we're going to assume 0 volts flow through our small signal. And so that gives us a short. So our equivalent circuit will actually look something like this. Plus, minus 2 volts. We have a ground. We have our source terminal. And then we have our D. And then we have 10 volts. And then we have our gate. Okay, well, in this particular circuit, we have that Vs equals 0, Vg equals 2, which means that Vgs equals 2 volts. And so we're going to use our DC analysis heuristic. So first we're going to assume saturation. Which will give us that ID equals K over 2 VGS minus V threshold. And K is 2, V threshold is 1. So we have 2 over 2 times 2 minus 1, which will give us 1 milliamp. So remember that this is milliamps per volt squared, and all of these things are in volts, so the volts squared cancel and you're left with 1 milliamp. Okay, so now we know the current, so now we need to actually confirm that we are indeed in saturation. Well, the voltage VD here is going to be 10 minus ID, so VD RD, which in this case is 10 minus 5 kilo ohm times 1 milliamp, which is equal to 5 volts. And so we have that VD minus Vs, which equals 5 minus 0, and that's VDS, is less than, or is greater than, VGS minus V threshold, which is actually equal to 1. And so indeed, we are in saturation. Okay, so we got that capital VDS is 5, and if you recollect in our previous, using our load line analysis, that's the same thing that we got in the previous lecture. So now that we have our, we know that we're in saturation and we know that VDS is 5, now we're actually going to start analyzing our circuit. So now we're ready to plug that in to get our small signal parameters. So let's go to the next slide. Okay, so here I kind of rewrote the math. So we got 1 milliamp per ID, we got 5 volt for VDS, and VDS is indeed greater than 1, because this is 2 minus 1, and this is 5, which is greater than 1. So we are in saturation. Cool. Now that we know that we're in saturation, we're just simply going to use this ID that we calculated and use it to determine GM. So we have the square root of 2 times 1, which is going to give us 2 well, this is milliamps per volt. Because remember, this is in milliamps per volt squared, and this is in milliamps, so we get milliamps squared divided by volt squared. We take the square root, so we get milliamps per volt. Now to figure out ID, RO, we have basically 1 over 1,000 times 1 milliamp, which is 0.001, and that turns out to be 1 mega ohm. So 1 over 1,000 is just 1,000, and divide that by 0.001, well, that's just 1 million. So we get 1 mega ohm. Okay, so that gives us the two parameters that we need. So now we have that GM equals 2 milliamps per volt, and RO equals 1 mega ohm. So now we're ready to actually do our small signal analysis. Okay, so we got that GM is actually 2 milliamp per volt, and we have that this is 1 mega ohm. So now we just need to basically write out our circuit. So to do that, we just first start by shorting all capacitors and opening inductors. So there's none of these, so we're done with that automatically. There's no capacitors or inductors in this circuit. Now we inactivate DC sources, so we need to turn this capital VGS into 0, thereby inactivating it, so that becomes a short. This VDD is really plus, minus, and then a ground, 10 volts. So as a result, when we inactivate this, it becomes 0 volts, so this becomes actually a ground. Okay, and so now we're done inactivating all of our DC sources. And so now that we've inactivated them, we end up with the following circuit. So we have kind of a VGS here, plus minus. We have a ground, we have RD, and then we have another ground, and then we have this connected to that. Okay, now we're ready to actually plug that into our small signal model. So at our gate terminal, and this is our source terminal, and this is our drain terminal. So between the gate and the source, we have this little VGS small signal model, GS plus minus. And then the source terminal is connected to ground. And then between the drain and ground, there is RD. So here's the drain terminal. And then we have RD. And then this would be plus minus VDS, which is just the voltage between the drain and the source, or the drain and ground, because the source is grounded. This particular circuit would be called a common source amplifier because the source is the grounded terminal. In this lecture, we're also going to look at common drain and common gate amplifier circuits. In each one will respectively denote the terminal that is grounded. All right, so now we have this circuit. In the next slide, we're actually going to start analyzing it to determine our gate. Okay, so now we have here our circuit. So this is a little VGS plus minus. In particular, we want to know our gain, which is actually VDS over VGS. And remember that in the previous lecture, we graphically determined, or using our load line analysis, should be equal to -10. Now we're going to do small signal analysis to confirm that this is indeed correct. Okay, so let's look at this nodal equation here. So we have that GM VGS plus VDS over RO plus VDS over RD equals 0. And so that's going to give us that GM VGS equals -1 over RO plus 1 over RD times VDS. So I just moved all the VDS terms to the other side and factored out the VDS. And now, since we need the ratio of VGS to VDS, I'm going to divide both sides by this and divide both sides by VGS so that we get that VDS over VGS is actually equal to GM negative 1 over RO plus 1 over RD to the -1. This could be replaced with, this is just really RO in parallel to RD. So it's just negative GM RO in parallel to RD. So this denotes the equivalent resistance of RO in parallel to RD. Resistance. Okay, well, what is GM? GM is equal to 2 milliamps per volt, so 2 milliamps per volt. And then we have RO, which is 1 over 10 to the 6, and then RD, which is 5 times 1000, and then to the -1. This, if you plug it into your calculator, is approximately equal to 5,000. And so you have 5,000 times 2 milli, which is going to give you, and then there's a negative sign in front, sorry. So this is VDS over GM, over VGS, sorry. And so 2 times 5 times 10 to the 3, and this is milli, so the 10 to the 3 and the milli cancel, and you're going to end up with actually that all of this is just equal to -10. So indeed, our small signal analysis derived what we intuitively got, the result that we intuitively got last lecture. And this is actually how we're going to analyze circuits. So now we know what the gain is. So this is what we're going to call the open gain, or AVI, for our circuit. To determine the Thevenin resistance, we would actually look at what the input resistance is. We would look at what the input resistance is looking into the input terminal, which in this case is VGS. And if you look, Rn, well, in this case, it's an open circuit, so Rn equals infinite. And our Rout would be the resistance looking into this output terminal. And remember that when you find resistances looking into an output terminal, you deactivate all other sources. So in this particular case, you would assume that VGS equals 0, so that you can neglect this, and it turns out that the output resistance is RO in parallel with RD. So that would be Rout is actually RO in parallel to capital RD. Okay, so that's how you would define all of the things that you need to know about the circuit. For now, just don't worry about these last things I said. We're going to actually look at a ton of more examples, and we're going to go over these derivations. For now, we can just realize that we got the same number that we got last lecture for this very, very simple circuit. So here's the actual derivation in more of a clean form. And finally, we got our correct gain. So as you can see, my handwriting is not very neat. So that's why I try to also give you the slides with the typed up solutions. I just think you hearing me go through the process of thinking through a problem helps you out. And so that's why I try to write down every step. But I do realize that my writing is not the cleanest. And I hope that if you have any uncertainties of what I actually wrote, having it typed up on the next slide helps you decipher my writing, because I do realize that sometimes it can be a bit challenging. Okay, so let's continue with this. All right, so now we're going to actually look at a real implementation of these circuits. And so we're going to actually start going through different amplifiers. And for each of these amplifiers, we're going to go through these 3 distinct steps. And in particular, one thing that you will notice is that all of the amplifiers will have a base circuit that looks like our DC biasing network. So every time we analyze an amplifier, we're going to have to analyze that circuit that was introduced in the first 2 classes or the first week of classes. This is why it's important that you know how to analyze these 4 resistor networks, because it's essential for analyzing single stage amplifier circuits. Okay, so I'm going to go over the common source amplifier, but before I do, that's actually going to be in a separate video. And then I'm going to do the common drain amplifier in another separate video, and also the common gate amplifier. The reason I'm doing this is because if you have seen the recordings, these lectures have gone all 1 hour and 15 minutes, or our power hour for our Tuesdays and our power hour for our Thursdays. And so in a class environment, I'm going to go a lot slower because I have stopped to ask questions, and it's very likely that I will only have time to maybe go over one of these amplifiers in class, or at least this is what's happened in the previous semesters. And usually I just give the students the slides, and then they can go through them on their own. Ideally, by the end of these lectures, you should be able to analyze these things by yourselves. So it's actually a good exercise to try this on your own without watching the videos. That being said, for a lot of you, after you hear it being done once, you might still have some uncertainties or things that you don't quite understand. And so attempting analyzing these circuits before watching the videos will shed light into where you're not sure about something. And then you can watch the videos to fill in the blanks and actually kind of figure it out. And it hopefully will lead to better learning outcomes. Okay, but before I kind of start analyzing these circuits and I kind of separate this into separate videos, we have to know what we're analyzing. So for all three circuits, for the common drain, common gate, and common source, there's going to be a circuit model that will have an input and an output. And in this particular circuit, the model for our input is actually these two, this voltage, so ideal voltage source with a resistance in series. And then our model for our output would be this RL or R load. Now, if you think of this amplifier as your standard speaker system, this would be your microphone model. Microphone. And the microphone actually requires a little bit of current, and so that's why there's this little R signal. This R signal is usually small, and ideally it would actually be a short, or it would be zero. And then on the other side, well, you have a speaker. Well, that's your load. Most speakers tend to be like 5 ohms or 20 ohms. You can actually look this up. If you have a speaker, it will tell you what the resistance is associated with that speaker. And so that's another kind of, that's what you load the amplifier with. Of course, you might stick 5 ohms on this amplifier, you might stick 2 ohms, and when you're designing the amplifier, you don't know what's going to be connected to it. So these are not actually parts of the amplifier equivalent circuit. So we typically think of us connecting this to an RL, and then we connect this to an R sig, V sig. And so typically we will define two different kinds of gains, what we define as AVI, or the open gain, which is the gain that you would have when you assume that RL equals infinity, or RL is an open circuit. And then additionally, you will have a the gain of your circuit, so your actual gain, will contain RL in the equation, or a non-infinite RL. So if you're asked for the open gain, you just know, look at your gain equation and treat RL as being infinite. Most likely your gain equation will have 1 over RL in it, and so then you're going to get basically that that factor will become 0. And then same thing here, your gain of your circuit actually assumes that R sig equals 0. So that the gain of your circuit is this V in over V out, which typically will assume that R sig is 0. So when they're asking you for the gain of your amplifier, you can just plug in for R sig 0 or a short, which essentially what I'm saying is that your voltage source is an ideal voltage source. It doesn't have any resistance associated with it. And additionally, if they're asking you for the open gain, then you just plug in for RL infinite. Now, why do we distinguish between these two? Because when someone buys a circuit, they might have a really high quality source, which has an R sig that's like 1 ohm. And in that case, the actual V sig to V out will be very different than if they connect a really bad, not so good source, which has a R sig of 10 ohms. And so in particular, when we derive this input resistance, our voltage will be divided between these two. And so if R sig is large, then we're going to get a smaller gain. And so since we don't know what kind of source people are going to use to connect their amplifier to, we typically report the input resistance without including R sig, and we report our gain without including R sig, or setting R sig to 0. So what you can do is just analyze this circuit forget about everything I just said. Come up with your equation, and then at the very end set R sig to 0, and that's your answer. And same thing, if they ask you for the open gain, at the very end, set RL to infinity, and that's your answer. And then you don't have to actually think about these things. So when you derive this RIS and you derive this capital RO, you will always be setting R sig equal to 0, RL equal to infinity, and you will be setting, and to derive this AVI, you also need to make that assumption. So no matter what the problem says, if they tell you RL is 50 ohms, when you're deriving RO, AVI, and RIS, you should always be using 0 for R sig, infinite for RL, and you'll be fine. That's when you're trying to derive the circuit model. Now, if they ask you for V sig over V out, and they tell you a not finite RL, then you have to include it in your circuit, because they're actually asking you for this full link. Okay, so in the next few slides, we will derive a set of equations, which I will actually summarize in the next slide. And then I'm going to conclude this video, and then I'm going to have 3 separate videos. Okay, so here's kind of the summary of the 3 sub-lectures that I will post separately. In particular, for each of these circuits, we will derive equations for AVI, RIS, RO, and V in over V out, including an RL, which we're going to call AV. So remember, for all of these, you assume that, RL, so for these 3, you assume that RL equals infinite. So RL equals infinite. And then here, RL equals infinite. And then for the 4 of them, you're going to assume that R sig equals 0, R sig equals 0, and R sig equals 0. Once you have all of these parameters, though, if you have a non-zero R sig, you can just analyze this circuit to figure out what V sig over V out is. So even though you derive these things assuming R sig is 0, as you can see here, you can actually derive what the output is for a non-zero R sig. And in particular, what you will have actually is some nice relationships here, because if you look here, this is just a voltage divider. So once you know the gain, assuming RL is infinite, so these 3, the gate, assuming that RL is not infinite, is just simply the gain assuming that RL is infinite times the sum of the 2 resistances divided by the sum of the 2 resistances times RL, or the voltage divider. So the voltage drop between here and here is just AVI times VI. So the current must be AVI times VI divided by RO plus RL. And then the voltage across here is just the current flowing through here, which is AVI times VI divided by RO plus RL times RL. So once you know this parameter, it's very easy to actually get the non-open gain. Additionally, since this gain is actually V in over V out over V in, we can get that V sig for all 3 circuits over V in is actually going to be equal to, well, V sig, sorry, let me just backtrack a little bit. I got ahead of myself. So if you look at this circuit, it's also a voltage divider. So the voltage here is actually V in is equal to V sig divided by the total resistance, which is just R sig plus RIS times RIS. So once you want to figure out what the gain is, assuming that what V sig over V out is, sorry, what V out over V sig is, you just need to plug in basically this equation and then just multiply it by your gain AV. So you're going to have that V out over V sig is actually equal to this factor here times your gain AV. So you have AV times RIS divided by R sig plus RIS. So what I'm trying to say is basically once you have these four parameters, analyzing this the complete circuit to get V sig over V out is actually quite straightforward because there's a voltage divider at the input and there's a voltage divider at the output. So that's why we only care about deriving these parameters. The rest ones are kind of freebies. Okay, so in the separate videos, I'm gonna go over the derivation for each of these particular amplifier circuits. So the common source, the common drain, and the common gate. In each video, we'll separately derive these four equations for each particular circuit. Okay, thank you.